Okay, we'll continue on in Chapter 9 now. Chapters 9 and 10, actually. And so we are taking a shift in our statistical inference, and now we will be talking about categorical data. Okay, so Chapter 7, the t-test was all for numeric data. Everything, all of the variables we were measuring were numeric. With Chapter 9 and Chapter 10, we will be dealing with categorical data. Okay. And so our first inference for categorical data our first method will be the confidence interval for a population proportion. Okay, so when we were looking at Chapter 6, we created confidence intervals, and that was for the population mean. This time, because we're dealing with categorical data, it's going to be a population proportion. So it'll be something like, what proportion of the population is female? Or what proportion of the population has red hair? Or something like that, okay? This is categorical data. So this is what we're going to do, okay? Now, our book uses something, again, a little bit less common in the literature, and it uses the Wilson adjusted sample proportion. Okay, so our traditional sample proportion would be p hat, and this is y over n. Okay, you count how many people have red hair, you divide that by how many people total we have, and you get p hat is y over n. Okay, our text uses p tilde y plus 2 over n plus 4. Okay, and I understand why this might be preferred to use over p hat. The key difference here is that if you have something that's relatively rare, it's very possible that you take a sample and you get 0 of that thing. Okay, and in that case, your sample proportion would be 0. Okay, but it doesn't mean that that there's 0 in the population. Okay, so if it's like, what percentage of people have 4 fingers on their left hand or something like that, okay? You might survey 100 people, and all 100 people have 5 fingers on their left hand or something like that, okay? In that case, your p hat would be 0. What p tilde does is it kind of forces you to say, no matter what number it is, it throws an additional 2, but then it also throws an additional 4 in the denominator. So whether you have a p hat of 0 or a p hat of 100%, this kind of just takes it away from those extreme values. All right? So, instead of, so if you count 0 over 100, instead of getting of p hat equals 0, p tilde would be 2 over 104, which is 0.0192. Okay, so it kind of fudges the number a tiny bit, but you're allowed to do this. It's not cheating or anything like that. Okay, and that's because, you know, if you have p hat equal to 0, your standard errors and all of those calculations will be 0 as well, and that just becomes problematic. Okay, and so essentially I'm just going to cut to the chase, and I'm going to say your confidence interval, your 95% confidence interval for the population proportion p, okay, using the Wilson adjusted proportion, is going to be p tilde plus or minus 1.96 times the standard error of p tilde which is that, okay? Again, if you take another statistics class, kind of the quote more traditional, which you don't have to worry about, traditional method. I will not test you on the traditional method, but just in case, you know, if you take a class in the future and you look back on these notes, I don't know if that happens or not, but or just if you ever look back on your notes, it would be p hat, the traditional p hat of 1.96 times p hat times 1 minus p hat over n. Okay. Who knew that we could have all these different toppings on top of our p's? Yeah.
What, I'm sorry, what does y stand for?
Oh, the y would be the count of, you know, whatever count of your sample with a certain trait. Okay. With the quote trait. Or it could also be number of quote-unquote successes. Again, arbitrary label. So if you want to know, you know, what proportion of M&Ms are blue, it would, you pour out a bag of 500 M&Ms, you would count up how many M&Ms are blue, and maybe 93 of them are. Your p hat would be, I mean, your y would be 93, and your p hat would be 93 over 500. 18.6%. Okay, so this is what we have. So we can just do a quick example. Okay, so I'll just do that. All right, so what proportion of M&M candies are blue? Okay, so you know, you buy a bag of 500. Buy a bag of 500, you count 93 blue pieces. Okay, so we'll make a 95% confidence interval. And so that will be p tilde is 93 over 500. I'm sorry, what am I doing? 93 plus 2 over 500 plus 4. So 95 over 504, what is that? 0.1885. Okay, and then your 95% confidence interval would be So you just plug in all of these values. And what do we get? We get 0.1885 plus or minus. So I'm going to just do answer times 1 minus the answer. So if you plugged in 1885, it might be ever so slightly different from my number because I'm using the exact value of 95 over 504 divided by 504. We're going to take the square root of this number. So I have 1.96 times 0.01742. So I multiply this by 1.96, and I have 0.1885 plus or minus 0.0341. Okay, so let's try this out. 1885 plus 0.0341. So on the high end, I have 0.2226, and on the low end, I have 0.1544. So I would make up some statement like, I am 95% confident that the proportion of blue M&Ms is between 0.1544 and 0.2226. Okay. If someone asks, do we have evidence? How many colors are there? There's brown, red, yellow, green. There's orange and blue. Yeah? Okay. Okay. All right, so if somebody claims that 1/6 of the candies are blue, do we have evidence against that? So do we have evidence against the claim that 1 in 6 candies are blue? What would you say? So just FYI, 1 divided by 6 is, there's that number, 0.16666. So we're 95% confident that the proportion of blue candies is between basically 15.5% and 22%. Okay? So if someone says 1/6 of the candies are blue, M&Ms, they're all produced in equal proportions. Okay? They say 1/6 of the candies are blue. Do we have any evidence against that? We would say no, right? Because that value, 0.16667, falls within our interval. So that is a plausible value, okay? So we would say no. 0.1667 falls within our interval. So it is a plausible value. Okay. Does this prove that 1/6 of the candies are blue? No, it doesn't prove that it's 1/6 blue, but we currently have no evidence against that possibility. Okay. So far, so good? All right. So that is confidence intervals for proportions based on P. Yeah.
Would we do other confidence
Yeah, okay, we could. No. Well, so the thing is when you do the Wilson adjusted proportion, it's not technically plus 2 and plus 4. It's technically like plus 1.96 and plus 3.89 or something like that. It's and these numbers of how much you add is based on the percent confidence level you're going to use. Um, so yes, we can, but I feel like it's a little bit more trouble than we need to bother with, and there is a section in the book that covers it, but I'm not going to bother putting you guys through that. Okay. We'll get through the whole book, but that means we got to skip a few of the topics, which in my opinion is fine, because these topics, like, I've never encountered some of these things outside of this class and this text, and that's okay. I think the book is great. I really like this book, but some of the things I'm just like, whatever, okay. All right, so we're going to move on here, and okay, so just so this proportion business, confidence interval for proportion, it's great if there's only like 2 categories or just really 1 category that you're interested in. Okay, so here we might just be like, we have an obsession with the blue M&Ms. We want to know what proportion are blue. Okay, and so this essentially dichotomizes our data into things that are blue and things that are not blue. Okay, but let's say you were really interested in all of the colors of the M&M company, okay? And so there you want to, like, someone says, no, I promise you, 1/6, each of the candies are produced in equal proportions. So you're like, wow, is this really the case? Okay, so now you have 6 categories or 6 colors to worry about. And in that case, you could do 6 individual confidence intervals, but things get a little bit messy when you do that, because the confidence intervals kind of depend on each other, right? Like, if you have too many blue candies, then that proportion of excess blue has to come from the other things, because all the proportions have to add up to 1. Okay, so things get kind of messy. And so to cover this, trying to track multiple categories, we have what's called the chi-squared goodness of fit test. Okay, the symbol for chi-squared looks like a X, and it's pronounced chi because this is the Greek letter chi, not chi, which is more of a East Asian concept. Is that funny? Okay. All right. So anyway, so we got the chi-squared goodness of fit test, and so the idea here is, again, we have a categorical variable, and we have multiple categories. It could be used for 2 categories. It could be used for more than 2 categories. Okay, so we have categorical variable with 2 or more categories. Okay, and what we have is we've got proportions in mind for the distribution of these categories, for the distribution of data in the categories, I should say. Okay, so it could be whatever. It could be as simple as, for M&M candies, your null hypothesis would be something like all colors appear in equal proportions. Symbolically, we would write something like this: proportion brown equals 1/6, proportion red equals 1/6, proportion blue, I don't know, so they're all, etc., etc., etc. I don't want to write them all out, okay, until you get to, you know, whatever, all and the other colors, okay? All right, so that would be the null hypothesis, and then the alternative would be at least one of these proportions is wrong. Okay? Yes?
Wait, so the other side would equal orange, yellow, and...
Yeah, I'm sorry. I'll do it. I was feeling lazy, but I'll write them all out. Just we're not. So I'm gonna write them up here just because I'm gonna run out of space. So we got orange. What other colors we have? Yellow and green, right? Okay. So you'd have.
It's just all common, it's not...
Huh?
They're all just commas?
Yeah, they're all commas, because that's it, yeah. Okay, and then the alternative would be at least one of these proportions is wrong. Okay, if you have more than two categories, your alternative is always going to be non-directional, because we can't say, like, there's too many orange or something like that, okay? We just say at least one of these proportions is wrong. Okay, so if more than two categories, it's always a non-directional. Okay, it could be, you know, it doesn't have to be all equal. It could be something like the null hypothesis. You know, maybe in this situation we're talking about I don't know. We'll say handedness. Okay, so maybe someone claims that 1 in 6 people are left-handed. I have no idea what it is. Okay, so we're going to say the proportion of left-handed is 1 in 6, and we're just going to split the world into left and right-handed. Will be 5/6. Okay, so you don't have to have equal proportions. The alternative, maybe someone says, oh no, it's not 1/6, it's less than that. Okay, so here we would say left-handed, we could say is less than 1/6, because in this case, if there's too few left-handed, then that means the right-handed must be greater than 5/6 if that's the case. Okay. And if you have just a dichotomous thing where you're either left-handed or you're not left-handed, all of these statements essentially become implicit. Okay, so if you only have you're either left-handed or you're not, these are implied, so you don't even have to bother worrying about this category over here, or writing these statements out if you don't want to. Okay, so these in a dichotomous situation, the complementary statements are optional. Okay, question.
Since they're complementary, is it a true statement to say that we could write or switch them out? Like
Yeah. If you wanted to say the probability right-handed is 5/6, or and the alternative is that it's greater than 5/6, that's totally fine as well.
What about mixing them up, like probability left-hand is 1/6?
That's ill-advised. If you're going to do that, then you should write out both sides of the complementary thing. Okay. And this is the only situation. So if you only in situations where you kind of have this dichotomous thing, can you have directional alternatives. Okay. So only when you have two categories can you have a directional alternative. All right, is this okay? Okay, so then let's do our test here. Okay, so let's say you gather your data. Okay, and so I don't know. We'll do our M&Ms. Okay, well, you know what? We're gonna do Reese's Pieces because there's only 3 colors in Reese's Pieces. All right, so with Reese's Pieces, we're gonna say our null hypothesis is that they come in orange, they come in yellow, and brown. And I don't know, do they appear in equal proportions? No. All right, they do. Under our null hypothesis, they do, okay? When we gather data, maybe we find something different. Okay, so this is our null hypothesis, and our alternative would be what? No, we can't do that. Our alternative has to be at least one of these proportions is wrong, okay? So only when you have 2 categories can you say one has too many, okay? If you wanted to do there's too many browns as the alternative, then it has to be, you have to dichotomize your data into non-brown candies and brown candies, okay? You can't have orange, yellow, and brown and say there's too many brown candies in our thing. So the alternative would be at least one of the proportions is wrong. Okay. All right, and then okay, so let's so we gather our data, and so we look at the color of the candy. We have orange, we have yellow, and we have brown. Okay, and then we'll count them. I don't know how many. We'll say we counted 35 orange pieces, 40 yellow pieces, and 42 brown pieces. Okay, so what is this? We have 35 plus 40 plus 42. We have a total of 117 pieces of candy. All right, does this mean, okay, what we observe here, do our candies not show up in equal proportions, okay? Does our data support the alternative hypothesis? This is essentially what we're asking. Okay, so what we do is essentially we're going to compare our data to what we would expect to see if the null hypothesis is true. Okay, so we will compare our data to what we expect to see if the null hypothesis were true. Okay? So what I'm going to do is I'm going to create a column over here that's going to be called expected. and it's expected if the null is true. But from here on out, I'm just going to call it the expected data. All right. So if the null hypothesis were true, and we observe a total of 117 pieces of candy, how many of those pieces should be orange? So we would do 117 divided by 3, and we would expect to see 39 pieces to be orange. Okay? And we would expect to see 39 pieces to be yellow, and we would expect to see 39 pieces to be brown. Okay? Now, it's totally okay if your expected values have a decimal, okay? So just, so in our case, coincidentally, we did not get decimal values, but it is okay to have decimal values in the expected column. Okay, is this all right? Where I'm getting these expected values? Okay, and so our chi-squared statistic is calculated as such. Our chi-squared is the sum of our observed minus our expected. So we're taking the difference between observed minus expected. We're going to square that difference and divide it by our expected count. Okay, and then we add this up for all values. Maybe I'll put that up there. Okay, so for our data, we're going to do this for all three of our categories. We're going to say 35. What we observed was 35 orange candies. I expected to see 39 orange candies. I'm going to square that and divide by how many orange pieces I expected to see, which was 39. I saw 40 yellow candies. I expected to see 39. Okay, so I'm going to have 16 over 39 plus 1 over 39 plus 9 over 39. Is that right? So I have 26 over 39. My chi-squared statistic is 0.667. Okay, so there we go. At this point, we're going to look up our chi-squared statistic in the chi-squared table. The chi-squared statistic depends on degrees of freedom also. Degrees of freedom here is the number of categories minus 1. So here we've got 3 categories of candy colors, so we're going to have 2 degrees of freedom. Let me just slide this up here. Okay. So when we do this, what do we get for our tail area? What we find, whoops. Okay, so we're looking at the critical values of the chi-squared distribution. We got 2 degrees of freedom. The first test statistic, that critical value that appears there, is 3.22, and our critical value, or our test statistic, is 0.667. So what does this tell us? It tells us that our tail probability is greater than 20%. Okay, so our tail probability is greater than 20%. Okay, all of these are non-directional p-values. Okay, if you have a directional p-value, then you have to take our column headings and divide by 2. That's what it says. So our tail probability is greater than 20%, which is our p-value. Our p-value is greater than 20%. Okay, so we would, what is our conclusion? Reject or not reject the null? P-value is greater than 20%. So assume alpha is 5%. So when your p-value is, yeah, so our, if we use alpha equal to 5%, our p-value is greater than alpha. So we do not reject the null hypothesis. Okay? Don't say we accept the null hypothesis. We say we have no evidence against the null hypothesis. Okay, so we say we have no evidence against the null hypothesis. We can never accept the null hypothesis. Only until we observe the entire population can we say that the null hypothesis is true. Until then, it's always just a matter of, I've got nothing to, we have no evidence against it, okay? So we have no evidence against the null hypothesis. This means, in the context of this all-important Reese's Pieces color candy proportion question, what does this mean? This means we have no reason to believe that the candies are not produced in equal proportions. Okay. Is that okay? Okay. All right. Well, if we're feeling okay with this, I'm gonna move on, and we'll cover chapter 10, which is going to be the chi-squared test for independence between two categorical variables. Okay, so this is often we just abbreviate the chi-squared test for independence. Okay, and so here, so the key difference between the chi-squared goodness of fit test and the chi-squared test for independence is that the chi-squared, this test looks at two categorical variables. Two categorical variables to see if there's a relationship between them. The compared to the goodness of fit test, which I'm going to just... The chi-square goodness of fit test looks only at one categorical variable. And tests to see if kind of preset proportions fit the data. Okay, so that's where the word goodness of fit test comes from. It's to see how good or how well the data and the proportions fit each other. Over here, we're testing to see if these two categorical variables are independent or not. Okay? So, let me look up something here. We'll look up Titanic survival data. Okay, so here we go. Can I just copy this image? You know what, I don't want to do that. Okay. I'll just rewrite this data thing. Okay, so we're going to look at Titanic data. All right, so in case you've been unaware, there was a boat. Well, I just remember seeing an article where it was like, people tweeted like, the Titanic was a real thing. Yes, it was a real thing. Okay, all right. So it was a big cruise liner, and there were 2,200 people on the boat, and the boat sank, and a lot of people died, and there was a movie about it. Well, several movies, and there's a fictional one that won many Oscars. It's a great movie, by the way. I saw it when they re-released it in 3D also, and it was like, okay, anyway, it was pretty cool in 3D too. All right, so here we got this this data set. Okay, 2,200 people aboard. You know, most of them were men. We had some women, and you know, when it sank, you know, they said things like women and children first, and we can see, you know, if that was true or not. All right, so you know, when we look at this data and we see, you know, what proportion of women died and what proportion of men died, we can see very clearly that there's a relationship, right? That if you were a woman aboard the Titanic, your chances of survival or being put on a lifeboat was much higher than if you were a male aboard the Titanic. But we can use statistics to say this is not a result of random chance, but rather that there was some effort put into something, okay? All right, so here, our null hypothesis would be that gender and survival are independent. Okay? Or in other words, we can do this symbolically, and we can say the probability of however you want to say it, survival given female would be equal to the probability of survival given male. Okay? If this equation holds true, then that means gender and survival are independent. Okay? And there's multiple ways we could write this, okay? Or we could write probability of what? Female given died is equal to probability of female given survived. This is another way to write the same thing. Okay? But either way, however you want to write it, okay? And then our alternative hypothesis could be survival rate for women is greater than survival rate for men. Okay, and so this would be probability of survival given female is greater than probability of survival given male. Okay. All right, so we can test this out. We can do the chi-squared test for independence. So we have two categorical variables, right? Our two variables are survival and gender. And we want to see, is there a relationship between these two variables? So this is the question we're asking. This is our data. All right, so to test this out, what we're going to do, whoops, that's not what I want to do. This is our data. We're going to compare our data to what we expect to see if the null hypothesis were true. Okay, so this, I'm going to write expected data, or I would say expected counts if the null hypothesis were true. Okay, so this is going to be so I'm going to just write died, survived, female, and male. Okay, so I'm going to just fill in the margins first. Okay, so if survival and gender were independent, okay, we can look at how many people died, and there was 1490, right? And we would expect, whatever percentage female exists, we would expect that percentage females to have died, and whatever percentage of males to exist, we expect, that the percentage of those who died, that percentage to be male as well. Okay, so we can look at something like percent female, and this would be 470 over 1731, right? So this is the, or not percent, I should say proportion female. Proportion female is 470 over 1731, and so, oh, I'm so sorry. Yeah, what am I doing? 470 over 2201, I apologize. Okay, so 470 divided by 2201. Okay, so 21.5%. Okay, 21.35. So 0.2135, etc., etc., etc. Okay, and then so we would expect this number out of the 1490. So then the expected number of females to die would be equal to 1490 times, 0.2135, where I can just write 470 divided by 2201. Does that make sense? Okay, so I would just take that and I would multiply that by 1490, and so I would expect 318.17. So I'll write this over here. So I'm expecting to find 318.17 females to have died. Okay? And then so I can do the same thing for the proportion to survive, expected number of females to survive. Would then be what? What values would I multiply here? 711 times 470 over 2201. So I can do 711 times 470 divided by 2201, and I get 151.83. Okay. Now, to be truthful, this calculation was actually kind of unnecessary, because once I knew 318 females are expected to die, and I know that this row has to add up to 470, I could have just done 470 minus 318.17, and I would get this number. Okay? And if I know this number plus this number has to add up to 1490, I can get this number as well, just from subtraction. So I would do 1490 minus 318.17, because I know that these two numbers have to add up to this. I would get 117.83, and over here I know that 711 minus 151.83, 559.17. Okay, so actually as soon as this number was set, the other three numbers are locked in as well. Okay, so actually that points out in this table we have 1 degree of freedom, because really as soon as this one number, which is kind of the only one that, as soon as one number is set, all three other numbers have no freedom in what they can be. Okay, so this table has 1 degree of freedom. Okay, so anyway, this is what we saw. This is what we would expect to see if gender and survival were independent. Okay, and so our chi-squared statistic is the same of observed minus expected squared over expected, and we do this for all of the internal cells. Okay, so it would be what we observed, 126 minus what we expected to see, 318.17 squared over 318.17 plus the next cell, it doesn't matter, as long as you do all of them, 151.83 squared over 151.83, and then 1364 minus, wait, I added something up wrong here. 1490 minus 1171. Okay, I'm like, something is wrong. Okay, I have to, thank you. Okay, so 1364 minus 1171. All right, so you do all of this. 367 minus 559.17 squared over 711. Okay, so when you have 1 degree of freedom and you do a chi-squared independence test for independence, all of the numerators are going to be equal to each other. That's one of the side effects of having only one degree of freedom. So all of these will have a difference of 192.17, because this is, we're seeing 192.17 too few females who died, which means we're seeing 192 too many over here, and 192 too many over here, and 192 too few over here. So all of these will have 192.17 too little, and then so I would do that divided by 318.17 plus answer squared over 151.83 plus answer squared over 1171.83 plus answer squared divided by 700. No, not 711. 559.17. Gosh, I'm making all sorts of mistakes here. 559.17. Okay, and I add this up and I get this ridiculously large 456.85. That's my chi-squared statistic. Is this okay? I guess I should write kind of the formula for the expected kind of a quick way to do this is to say you do your column total times the row total divided by the grand total. Okay, but you can see that this is exactly what we did. We just said the proportion of females is 470 over 221, 2201, which is the row total divided by grand total. And we said, okay, if that's the proportion of females that exist, we expect that many of people who died to be female. So we just multiplied 1490 by that, which is effectively what we've done here. Okay, so my chi-squared statistic is 456.85, and we have 1 degree of freedom. Okay, degrees of, well, yeah, that's fine. So if you have a 2 by 2 table, you have 1 degree of freedom. Okay, so we go to our chi-squared statistic table, and we see the largest number we have listed is 15, and we're out at 456. Whoops. Okay. We're at 456. So we're going to what happens? So our chi-squared is equal to 456. From the table, we know that the probability is less than 0.0001, which is what we have here. And in fact, we have a directional alternative so our p-value is even half of that, right? Half of our tail. So we get our p-value is less than 0.00005. Okay, so all in all, we're going to reject our null hypothesis. Okay, and we say we have evidence that the survival rate for women aboard the Titanic is greater survival rate for men. Okay. Let's just think about what the p-value means. Okay, so what does our p-value mean? So it's saying that, theoretically, by random chance, anything is possible, right? Theoretically, by random chance, it is possible that there just happen to be more women aboard the lifeboats than the men from random chance alone, okay? But what this is saying is that the probability for this result to have happened from random chance alone is less than this. In fact, much, much less than this, because our test statistic is ending up at 456. So this is like 1 in a, 100 billion or something like that, okay? It's an incredibly small value. So our results, we have evidence that our results were not from random chance. Okay, so what does our p-value mean? So, if we think about it, so it is technically possible that by random chance, more women boarded the lifeboats and survived. Okay. However, the probability of observing our data from random chance alone, however, is incredibly small. Okay, so we say we have evidence that our data is not a result of random chance, not a result of random chance, and instead that something happened that increased the survival rate of women. Okay. Statistics doesn't give us any insight into what happened, why women it gives us no insight into causal information. Okay. Historic accounts indicate that this notion of women and children first, and that this priority was given to women and children is the reason for this. So because of that, we have an idea of what happened, but the statistics, the data itself, this does not provide that insight. Okay, so we can't make causal inference. Okay, because as far as the data goes, someone could, if they could look at this and just say, oh well, women are more apt for survival in, I don't know, cold water. Okay, which might actually be true. I don't know. I don't know, but it probably wouldn't account for this kind of difference. But there is. Okay. What else do I need? Oh, okay. So there's one more thing. Okay, so this test for independence can be applied to what's called an R by K table. And so this is like if you have category 1, category 2, category 3, and then you have category A, category B, and category C. Etc., etc., etc. Okay. So let's say you have all of this. what happens, okay, so the mechanics are the same, okay? It's just more tedious. Okay, you create your expected table. And then you do chi-squared is observed minus expected squared over expected. Okay, you add all of those up for all internal cells. And then your and you just look this up in the chi-squared table, but your degrees of freedom is equal to the number of columns minus 1 times the number of rows minus 1. Okay. But everything else is done pretty much the exact same way. Okay. There is I guess a warning here, and that is, believe it or not, there is a central limit theorem underlying the mechanics of this. Okay, the chi-squared distribution is the distribution of the square of a normal variable. So if you have a random variable that follows the normal distribution and you were to take that value and you square it, you end up getting the chi-squared distribution. Okay, you don't have to worry about the theoretics behind this, but there is a underlying central limit theorem, and so what we say is that to use the chi-squared test, the expected count, and this varies from text to text. I think our text says you make sure the expected count is at least 5, but let me just make sure. Chi-squared test. At least 5, yeah. Okay. So, yeah, conditions for validity. We should all of this. Okay. So to use the chi-squared test, the expected count for all cells in the expected table should be at least 5. Okay, and some texts will say 10, but ours says should be at least 5. Okay, and so what do you do if you don't have 5? Well, you have a few options. Okay, you can collapse categories. All right, so you can, we could say like is I don't know, maybe. So we could imagine some table that splits out by different ethnicities, okay? And so maybe a certain ethnicity, you just don't have very many people in that ethnicity. So what you can do is you can kind of combine certain groups together, okay? So if you have like a few ethnicities where there are a few counts, you can kind of just combine them together and say this category now is this conglomerate of these other ethnicities or something, and then that way you can kind of increase the expected counts so that they're all over 5. Okay, so that's one way to handle it, is to just kind of collapse categories or combine categories together. And then the other way is you can apply the non-parametric Fisher exact test. Whoops, something happened. Okay, so we have there is a Fisher's exact test, which I don't know where it went. Okay, but that can also be applied, but we're not going to cover that. Okay, so all we're going to say is if you're going to use a chi-squared test, you should make sure that that it's at least 5 in your expected counts table. Okay, we will end there. We'll see you guys next week.